Hello everybody, good day. Uh, Today we are going to see a very interesting simulation connected with the same induced draft and radial impeller. The previous simulations we had performed random responses. We had also done frequency response simulation. We had also done model dynamics. So as I mentioned earlier, uh, let's revise what exactly we had done. The preliminary simulation was connected with structural deformations. We had performed a structural simulation and we had analyzed the cascade impeller, which was the actual impeller, and that had a lot of weight optimizations to be performed. And there were a considerable change in the design from the client suggested model. And the client also suggested for research to understand the differences between the casted and the fabricated impeller. So the original casted impeller was reconstructed using a CAD software, and from the basic simulations there were a few optimizations, iterations done on the structure, and thus the thicknesses and the other geometrical parameters related were changed, and then we had found out the deformations. The client specified model operated in three rotational velocities, which was 800 rpm, 1000 rpm, and 1200 rpm. So we had performed the structural simulation, and we found that the stresses were within the yield point, as well as the deformations were about 0.05 mm, and which we even concluded that the system is safer. However, we also discussed that since this particular structure experiences a lot of vibration, and it experiences a lot of cyclic loadings, repetitive loadings, we decided to go to the next set of simulations, wherein we had to identify what were the natural frequencies. So we found out the natural frequencies. So we extracted the first 10 natural frequencies, and we found that the first 6 modes were 0, and the 7th mode onwards till the 10th mode we extracted 3 frequencies ranging between 250 hertz to 340 hertz. And we also discussed that how does the structure behave when it was subjected to an operating load. So the operating load is nothing but the same range of revolutions, I mean the rotational velocities, 800 rpm, 1000 rpm, and 1200 rpm. So the structure was again modeled, the finite element model was performed with the basic considerations, the load considerations, the boundary conditions, etc. So the bolt locations were all constrained by releasing the axial rotations, and then forced frequency response was found out, simulation was performed, and then we extracted a set of 10 frequencies, and then we found that few frequencies were matching with the natural frequencies. So we decided that we change the dimensions, the geometrical parameters of the system, and we made the thicknesses, the members, the vertical members and the horizontal members. The vertical members, the blades or the vanes that we call, and the horizontal members, the plates, the top and the bottom stiffeners, and the top and the bottom shrouds, and the top and the bottom crown, and then the central disc shroud, which was reinforced with two plates on either side and then bolted. So this was supposed to be a rigid system. So we also concluded the rigidity would increase torsion on the structure, and because of torsion there could be a lot of stresses that would be dominated, and these dominant stresses would be the tearing stress, and which can tear up the structure. So hence what we decided is we decided to go for a change in the stiffness parameters of the structure, and we also tried to arrive at a suitable property, the material property, and we concluded upon the simulations by keying in some damping values. So we call it as the model damping values because we perform the model simulations. And now by applying the model damping values and by linking the system, okay, to the forced vibration or the forced model dynamics, we found out that there were few more alterations to be done with the geometrical parameters which we had performed. Now, we found that the system was safer, and we decided to get into the next set of simulations where we are supposed to be studying the fatigue and the durability parameters. So whether the structure is going to be safer in terms of repetitive loadings, or the structure is going to be safer because of any external load conditions or external excitations. So as I told you, these structures are connected. These structures are generally used in the heavy engineering systems, and we can say like a few examples or instances would be in power industries or cement factories or any other industries where it's connected with noxious gas and high temperature gases, okay, which needs to be eliminated from the bottom environment, and then it is supposed to be pushed to the upper atmosphere and then exited. Now these structures are going to experience some external disturbances also, external vibrations also, and apart from that we are also forced to understand the stability. Now for a single cycle probably the structure might be safer, or maybe up to 100 cycles, load cycles, the structure could be safer. But then what would happen if the structure repeatedly experiences the same kind of loading conditions? Or what would happen if the structure is excited by a response or a signal or a pulse which is very unusual, maybe something like earthquake or a seismic impulse. Now the seismic forces or the impulses are going to be really huge. It would be in the range of 10G or 12G or 15G, which is almost about say let's say it can also be varying in the form of Richter scales about 4 or 5 or 8 or 10. So now these impulses or power spectral densities we call it as PSDs or spectrum. These kind of spectrums with higher amplitudes, okay, in a short duration, repeatedly will be able to destroy the structure. So now let's try to find out how the structure is going to respond to that. So we have already performed random responses, and we have found out how the system behaves. So now what we are doing is we are performing a dynamic analysis, a transient dynamic analysis with respect to time. So now we are trying to find out what would happen to the structure when this particular impulse, an excitation. So we are giving a sinusoidal pulse, and this sinusoidal pulse will be remaining there for a period of, say, about the amplitude is about 9.8 meter per second square. Okay, so now that is g, that's the acceleration due to gravity. Now this can be increased to 2 times g or 3 times g or 6 times g based on the pulse. So now it's about the conversions. Let's say that there is a strong earthquake or a seismic load that has affected the structure, maybe the foundation of the structure. And this particular structure, the impeller is mounted onto a pedestal with some anchor bolts. Now, the earthquake, the sudden impulse of the earthquake, that spectrum is going to be connected to the foundation, which means that directly strikes the foundation, and from the foundation it goes to the anchor bolts, and to the anchor bolts it gets transferred to the impeller. Okay, so now we also need to understand, like, is there any other members that need to be designed in order to take these earthquake loads or seismic loads or any other vibration. So we try to design dampers. Okay, maybe some neoprene dampers or some Teflon dampers, depending upon the intensity or the application. So here we are applying a G force. It's a single G, that is 1G, 9.8 meter per second square, and we are applying it horizontally. And you can see the global axis. This is so here you will find the x coordinate, the y coordinate, z coordinate. The impeller, the shaft axis is along the z axis. So we are applying a certain intensity across the direction x, and then that is 9.8. Okay, so we are applying the excitation type is an acceleration. Okay, so now a g force is applied. Now there is a time for how long is this particular g force acting on the structure, because that is what we call as excitation, the base excitation. So we are applying a factor. This is the sinusoidal form. It's a half sine wave what we are giving, and we define that the amplitude factor is 1 and the start time is 0 and the duration is about 0.1 seconds. So now in 0.1 second, what would be the response felt by the structure? What is going to be the response of the structure? So that is what we are going to perform. So now, performing this particular simulation by giving the time functions as well as the excitations, the g force, we are giving a setup. We are defining the time in seconds is about 1 second, and then we have the frequencies, the range of frequencies, whatever forced frequencies we have performed, not the natural frequency, the operating frequency. This operating frequency is ranging between 120.88 Hertz to 480.16 Hertz. Okay, so this is the frequency range, and within any within any of these ranges, this pulse of 1 second, that is the pulse what we saw there, the time function, that pulse is applied for a duration of second, and we are performing this simulation onto this. So once we perform a simulation, we will be able to understand like how the displacement is going to be. So it is evaluating the peak responses that is going to come on the structure, and how, in what duration is this response going to behave. Okay, so this is how it's going to be. You can see that, see, this is how the structure, in that 1 second, a pulse of 1 G when applied for 0.1 seconds is going to behave this way. So this is going to be the displacement, and you will find it is about 0.003 0.0015 mm. That's okay. Now let's find out what are the von Mises stresses. Now, because of that particular excitation of 1 G force, there is going to be a stress induced on the structure. So let's find out like what is going to be that von Mises stress. So now, if the stresses are again within limit, we can say for 1 G force, the system is going to be stable. Okay, so here we are able to find that the von Mises stress is about 0.75 Newton per mm square. That's pretty less. It's very less. For G force, it is very less. Now, if the G force is increased to 2.5 G or 3 G or say about 5 G, this will definitely increase. There are the members, these members are going to experience a heavy stress. Okay, so now you will find, yes, this is how the stress values are going to act. Yes, so now let's see like what are the velocity magnitudes. What would be the velocity with which the entire system is going to move? Because that is that is something which is very important, because we have given a 1 G load to this, and then here we find it is 0.0008 meter per second. So this is a very less response, I mean value. Yes, so that's it. That's one pulse. Okay, so now what we'll do is let's try to find out what is the acceleration magnitude. So we have applied a 1 G force, okay, with a pulse factor of 0.1 second, okay, and then the entire structure is going to operate for 1 second. So that is what we are seeing here. So here you will find the acceleration here is 0.1 meter per second square. The system acceleration. If 9G is the kind of, sorry, if 9.8 meter per second square, which is equal to 1G, is the kind of force, the excitation imparted to the structure is going to respond by 0.1 meter per second. That's going to be the acceleration, the jerk, the inertia. That is what we call here. Okay. So now let's try to find out like how the responses are going to be. How the responses are going to be. So let's say that the internal part, the disk part. So this is the internal disk part, and what is going to be the displacement in magnitude. So let it evaluate. It will evaluate and give us what exactly is the deformation, the deflection that is going to occur on that particular central disk. So here you will be able to find out the response. So the response is nothing but it's a pulse. So this is the pulse. So it is about 0.000105. It's very small. So that is in 0.1 second, 0.15 seconds, we will have a bigger amplitude, and the biggest amplitude itself is about close to 0.00. That is almost in microns. Now let's see what is going to be the von Mises stress. So we have found out what is the deformation, the deflection response, and let us see how the stress is going to vary all throughout that particular central disk, how the stress values are going to vary. And so these are very, very important parameters which we need to determine, because based on these parameters, okay, we will be able to parallelly conduct a test, and the test will be performed with suitable strain gauges, accelerometers, etc. And that will be happening in a separate part. So let us say this actual impeller, a single model, not a model, I mean the actual impeller is made by welding the plates, and then this impeller is suspended, and then the model frequencies are extracted, and based on that some random responses are done with the help of excitations, and these excitations are done through either sorry, using tuning fork or any other excitation procedures. And once all these things are performed, the data, whatever we get from the test lab or the test systems, okay, that is compared with the virtual simulation system. So this is what is called as the virtual simulation system, and these are correlated. The virtual simulation model and the test models are compared, and either of them is updated. So with the data what we have extracted from the test is going to be correlated with the virtual simulation model, and then that is going to get updated. So once all these procedures are done, okay, we call it as model updations. So this particular system, okay, when virtually performed, complete system is going to be virtual. We are able to replicate the model, and the same updations is done, and a n number of iterations can be performed through multidisciplinary optimization processes by giving suitable algorithms, and then the actual model, the most optimized model is achieved. So this entire platform is what we call as digital twin or digital twinning procedure. So now here we are able to see what are the von Mises stress and what is the stress value. So here we'll find it is about close to 0.065. Okay, that is for a single. We can increase the time, and then we can find out the time for simulation would increase, because here we are giving about 1 second and defining it as 0.15. So now for that 1 second, if we make it about 10 seconds, then accordingly the simulation time also will increase. So now let's see what is going to be the velocity magnitude for that particular disk. So now the velocity magnitude it is going to calculate, and this is going to generate a spectrum. Okay, so this is how we will find that acceleration g force whatever we have given to the structure with a rotational velocity of about 800 rpm. How this is going to excite the structure. So it is nothing but a model superposition. You already have a rotational velocity, and you also have a base excitation. So now there is a mode which is generated from the rotational velocity, and there is a mode which is generated from the external excitation or base excitations. So these base excitation, these kind of simulations are even performed in structural engineering, in most of the structures, the building structures, the cooling towers, for any bridge structures, for all kinds of structures, a seismic analysis or earthquake analysis is performed exactly this way. So this is called the direct transient formulation or method with which we are finding out the spectrum. So here we will find the velocity spectrum. So this is how the velocity is going to be. So the peak velocity is here, and the magnitude is very less actually, because it's for a very small force. G force is nothing but it's the weight. That's all. Now if the G force is going to increase, say about 10G, 12G, 15G, that is when these values are going to be abruptly increasing. So let's see what is the magnitude of acceleration for the same disk. So likewise, we will be able to find the deformation, the stress values, the acceleration, the peak RMS, that is the root mean square velocity, and the root mean square uh, uh, acceleration part can also be determined through this process. And from this process, we will be able to finally ensure the stability, the complete stability of the structure. And now here the acceleration values, whatever we get, the excitations. These are the excitations, okay, the random vibrations, whatever you are able to see here, the peak. Yes, so these are the random vibrations, the excitations. So these excitations are going to be the input values for the test simulation. So the pulse, this particular impulse is extracted, and this impulse is going to be given as a excitation to the structure. Okay, so now we have found out how the acceleration plot is, and how the velocity plots and all those things are found out. Now the similarly we'll be able to find it out for different regions. So now this is the region where the shaft has got a direct influence. Okay, so now let's consider this particular part, that is the region exactly where the shaft comes and rests. Okay, it is mating with the shaft. And now let's try to find out what is going to be the response on the blade. Yes, so this is going to be the response on the blade. And now what is going to be the response on the top stiffener? Yes, this is the top stiffener. So you get a response like this. And then what is the response on the shroud, the bottom shroud? So this is going to be the response on the bottom shroud. And now what is going to be the response on the crown, the top crown, where the torsional stresses are dominant. Okay, so now this is how the response behaves. Now let's try to find out the yes. So for all elements, we have found out what are the stress, sorry, the acceleration magnitude. Now let's try to average it. That is the average of the entire structure, the entire system, because we have considered all the elements here. That is the crown, the shroud, the vertical blade, the horizontal stiffeners, the central disc, and the shroud. So all structures are considered. Now if we want, let's consider this also, and let us consider this, and let's consider this. Okay, let's consider the top shroud. Okay, so yes, so now once we have yes, let's evaluate the average. Now the average of the entire structure, we are able to find the peak frequencies are here, and we know that this is the excitation. This is the excitation, and because of the damping factors, whatever we have, the 0.3, 0.03 is the model damping factor which we have imparted to the structure, and now that model damping is trying to dampen down the material damping. This is called the material damping. Okay, so this is how the power spectral density, the random vibration simulations are performed for a structure. So this is exactly the same, even if it is a chassis of a automotive car, or even if it is a turbine, or even if it is an impeller, or even if it is a building structure, a multi-story structure, a multi-story building with maybe about 16 stories or 18 stories or 25 stories, whatever it is. And any portal frames can be simulated, and bridge structures can be simulated, the cable swayed structures can be simulated, suspension bridges can be simulated, any geotechnical structures can also be simulated. Okay, so now these kind of simulations are performed even on very uh, special kind of environmental catastrophes. Say, for example, tsunami. Simulation of tsunami can be done similarly, because these are all the waves and oscillations. I mean, we have the uh, excitation forces developed because of the earthquake, and because of the earthquake, how the plates are getting moved, how the plates move over one another, how the tremors are caused, what is the excitation caused by the tremor, measure that, and the same excitation is imparted to the building structure. So we have the foundations and the columns connected to the pedestal, and the pedestal to the foundation. The it can be a mat foundation, or it can be a raft foundation, or any kind of foundation. Finally, the excitations will be applied onto the columns, and now from the columns, those columns that are pinned and those columns that are fixed. Okay, so depending upon the boundary conditions, we can apply the excitations, and then we can find out how the structure is going to collapse because of uh, the responses. I mean, because of the earthquake simulations. So what we can do is we can identify the power spectral densities, the variations because of the excitations, and then we can try to simulate it in the test. So that is the basic reason we say a test model and a finite element model, or a virtual simulation model, the digital simulation model, is compared to one another, it's correlated and then updated. Okay, so this is the end of our complete simulation on the impeller, and the next episode I'm going to come with a entirely different structure. Let's try to work on a multi-story structure. Let's try to join hands with a few civil engineers and try to perform some simulations, very interesting simulations. And we will start from the basic structural simulation. We will go to normal modes, frequencies, buckling of structures, and we will also find out the seismic simulation, the earthquake, and we will also identify, we will also try to model blast. Okay, what exactly happens when the structure is going to be blasted because of some bomb or explosives or anything. Okay, so thank you very much for your patience, and I would again try to request you that please subscribe and share the particular episodes whatever you watch, because these are very interesting videos, very simple, crisp, and practical. In a sense, it's very much practical oriented, and this is going to help every working engineers, and this is also going to give a good highlight on how the digital simulations are carried on, and how the what are the advantages of digital simulation, and how an optimization process is done, what are all the complex mathematics and statistics involved in optimization, and how we will be able to make the simulations very robust, faster, using graphical processing units or neural processing units, and how the entire system can be simplified, and using digital twinning procedures. So once again, subscribe, share, and please raise your valuable comments and queries, and I will be really happy to answer you. Okay, thank you very much.